students, physics class 1 lasers, in which we are going to study what is laser, introduction, interaction of radiation with matter, population inversion, laser action, construction of helium neon laser, construction of semiconductor laser and its applications. The word laser stands for light amplification by stimulated emission of radiation. Laser is a device that amplifies light and produces a thin intense beam of light that can burn a hole in diamond or carry signal of many different television pictures at the same time. Light is a form of energy that is released from individual atoms or molecules in a substance. To understand how laser works, it is necessary to know something about the nature of the atoms and their interaction and the other forms of energy. Interaction of radiation with matter. Light is a form of energy in the form of electromagnetic wave. There are three methods by which the radiation interacts with the atoms of the matter: spontaneous emission, stimulated absorption. Let us study spontaneous emission. So you all already studied this thing. The atoms in the excited state or higher energy level stays only for an average time of 10⁻⁻⁸ seconds. That is a very short interval of time the excited atoms stays in the higher energy level. Thereafter, the atoms comes to the ground state automatically by emitting a photon of energy h nu. So this process is known as spontaneous emission. When an atom is excited to higher energy level, the atom in the excited state remains only for a short interval of 10⁻⁸ seconds. Then after, automatically it will come back to the ground state with the emission of a photon. Okay, so this process is known as spontaneous emission. Let E1 be the energy of the ground state, E2 be the energy of the excited state, and nu is the frequency of radiation, h is a Planck's constant. Then we all know that the energy difference between the two energy levels is emitted in the form of electromagnetic wave or a light wave, that it is known as E2 minus E1 is equal to h nu. Therefore, nu is equal to E2 minus E1 divided by h. In an assembly of atoms, in the sense when the electrons are excited to higher energy level, then we don't know how many number of electrons are excited to higher energy level and how these excited electrons come to the ground state. In the sense, which electron comes to the ground state, which stays in the higher energy level, that is very difficult to predict. So therefore, in an assembly of atoms, it is difficult to predict which atom may take a transition from E2 to E1. But probability of transition can be calculated. Okay, so let N2 be the number of atoms in the excited state and dou N2 be the number of atoms taking transition from E2 to E1 in the time t to emit a radiation spontaneously in a time dt. Therefore, rate of decay of atoms by spontaneous emission is equal to dou N2 by dou T. It is found that dou N2 by dou T is directly proportional to minus N2. In the sense, that is, the rate of disintegration of atoms is directly proportional to total number of excited atoms in the higher energy level, and it is shown by negative sign because the N2 value, that is the number of atoms, excited atoms value goes on decreases with increase in time. So therefore, we show it by negative sign. This equation can also be written as dou N2 by dou T is equal to minus A into N2, where A is known as probability of spontaneous emission or Einstein's coefficient or Einstein's A coefficient also it is called. Okay, let us study stimulated emission. In some elements, the energy levels are exist, that is higher energy levels are exist, in which the excited atoms stays at least 10 raised to minus 3 seconds, in the sense up to 1 millisecond. So it is a very long time. So these energy levels are known as metastable states. These energy levels are known as metastable states. Suppose the excited atom is in the metastable state, then a photon having energy exactly equal to the energy difference between the two energy levels. The incident photon stimulate the atom to move from excited level to ground level is known as stimulated emission. Here already the atom is in the excited state by the absorption of the some incident energy, and then it stays there for a lifetime of 10 raised to minus 3 seconds in the energy level, higher energy level, that it is known as metastable state. It does not exist in every atom, it exists only in some elements, and when the same frequency of radiation is incident, it stimulates the atom in the excited state to make transition to the ground state with the emission of same photon in the same direction. Okay, so that it is known as stimulated emission. When a photon of frequency h nu is incident, already the atom is in the excited state. It stimulates these atoms to make transition from higher energy level to lower energy level. Then in the next step we get two photons of having same energy, same frequency, same wavelength, emitting in same direction. That is the reason why the laser light emits. So in an assembly of atoms, again we assume that the population of the atoms in the excited state are more. In an assembly of atoms, it is difficult to predict which atom may take a transition from E2 to E1, but probability of transition can be calculated. Let N2 be the number of atoms in the E2 state, dou N2 be the number of atoms taking transition from E2 to E1 in time dt to emit radiation spontaneously. Therefore, rate of decay of atoms by stimulated emission is equal to dou N2 by dou T. So it is found that dou N2 by dou T is directly proportional to minus N2, or dou N2 by dou T is equal to minus B into N2. So again the same thing, it is directly proportional to number of atoms in the excited state, and the negative sign shows that the number of atoms are decreasing with respect to increase in time. So therefore we introduce the proportionality constant here, that is the B. So where B is the probability of stimulated emission or the Einstein's B coefficient. Okay, let us study stimulated absorption. So here in this case, the atoms in the ground state absorb the incident photon energy and make transition to higher energy level, and if it is higher energy level is a metastable state, again these atoms stays there for a lifetime of 10 raised to minus 3 seconds, that is in of the order of milliseconds. When the same radiation having same wavelength, same frequency made incident, then again due to stimulated emission a same photon is emitted in the same direction. Okay. The transition of atom from ground state to excited state by the absorption of incident radiation is called induced absorption or stimulated absorption. Let N1 be the number of atoms in the E1 state, N2 be the number of atoms in the E2 state. H nu is the energy of the incident radiation. So therefore H nu is equal to E2 minus E1. In order to make an atom excited to higher energy level, the condition is that the incident photon energy must be equal to the energy difference between the two energy levels. In the case 1, if N1 is greater than N2, in the sense the number of atoms in the ground state are more than the number of atoms in the excited state, rate of absorption of external radiation is greater than the rate of induced emission, so therefore intensity of external radiation decreases. So when the atoms population is more in the ground state, then absorption takes place and the atoms get excited to higher energy level. So induced absorption is more and induced emission is less. In the second case, if N2 is greater than N1, in the sense the number of atoms in the excited state are more than the number of atoms in the ground state, then the rate of absorption of external radiation is smaller than the rate of stimulated emission. So therefore the intensity of external radiation increases. So therefore amplification of light is possible only when N2 is greater than N1. In the sense, number of atoms in this excited state are more, then induced emission is more. Also, the intensity of the light also increases, that is the amplification of light also increases, which produces the laser light. Okay students, let us study population inversion. So population inversion is most important thing in the laser action. So without population inversion, laser action cannot be takes place. Population inversion means usually at room temperature the population of atoms in the ground state are more than the population of atoms in the excited state. So we have to invert this, in the sense we have to make that the population of atoms in the excited state must be more than the population of atoms in the ground state. So that process is known as population inversion. The amplification of light is possible only when the population of higher energy state is greater than the population of ground state. So this condition is called the population inversion. To achieve this condition, one of the higher energy state must be metastable state. Otherwise, it is not possible, because if it is not a metastable state, then the lifetime of the atoms in the higher energy state is just 10 raised to -7 or -8 seconds. It is a very short interval of time. The excited atoms come back to the ground state with the emission of same light. Okay, so if it is a metastable state, then the number of atoms in the excited state goes on increases and they stay there for a lifetime of 10 raised to -3 seconds, that is the milliseconds. So in this case the induced emission takes place. So due to induced emission, the light amplification is possible, that it is known as laser action, dear students. Let us study laser action. So in order to obtain the laser action, we already studied the population inversion is must and should in case of the laser action. The principle of laser is based on the phenomenon of stimulated emission of radiation. The photon emitted during the stimulated emission has the same energy as that of incident photon. So here the photon emitted due to stimulated emission has the same energy as that of incident photon. So it is emitted in the same direction and has the same phase. Thus the two coherent photons are produced. You can see this is the incident photon that stimulates the atom, due to which two stimulated photons gets. So the consider collection of atoms all in the metastable state. A photon passes the first atom causing induced emission and the resulting into two photons. Each of these two photons causing an induced emission, so that it is results into 4 photons. These 4 photons again make a induced emission, so causes 8 photons. So this multiplication of photon emission increases, results with the emission of same light with the same frequency, same phase and in the same direction. So that itself is known as laser action, dear students. Thank you. One more point I would like to mention here, dear students, that is condition for laser action. In order to obtain the laser light, what is the condition? At least pair of energy levels E1 and E2, in which E2, that is the higher energy level, must be a metastable state. It is must and should required. Then the second is the source of incident radiation whose energy must be equal to the energy difference between the two energy levels. That is the source of energy, in the sense, in order to make an induced emission, the incident photon energy must be equal to the energy difference between the two energy levels. And the third one is population of upper level must be greater than the lower level, in the sense the excited atoms population in the higher energy level must be greater than the, that is, ground state energy level atoms. Okay. Then the fourth one is there must be induced emission of radiation takes place. If the lifespan of the excited atoms in the metastable state is 10⁻³ seconds, then if you do not induce the atom to make a transition, after a lifetime of 10⁻³ seconds, it will come back to the ground state with the emission of normal light. So therefore, the induced emission is very necessary there. So therefore, the induced radiation must be takes place in case of laser action. These are the 4 conditions for laser action. Okay, thank you.